That means um, it meets the x-axis. Intercept means the point where it means this coordinate axis, x-axis. So they ask us to find x-intercept and show that the derivative is 0 at some point between the intercepts and find that point. So let's take the equation x square minus 3x plus 2 and make it equals to 0. And very clearly it has two factors, x minus 1 and x minus 2. When x equals 1 or when x equals 2, it meets the x-axis. So when it meets the x-axis, y coordinate is 0. So function value at both 1 and 2 are equal and equal to 0. Now, if I take a equals 1 and b equals 2, f of a equals f of b. So it in this case, we have all the conditions given in the Rolle's theorem. When x equals 1 and x equals 2, the function means the x-axis. So function values at those two 0. So by the Rolle's theorem, there is a in between 1 and 2 that the derivative is 0 at that point. That means this function has a relative extreme value, relative maxima or minima in between 1 and 2. So take this equation, take this function, differentiate it, make it equals to 0. Derivative of x square is 2x, derivative of minus 3x is minus 3, derivative of plus 2 is 0. So 2x minus 3. So derivative at c is 2c minus 3 equals 0 means x equals 3 divided by 2, 1.5. Exactly the middle point of 1 and 2, average of 1 and 2. So at that point, the derivative is 0. It has relative maximum. Now, if you want, you can check whether it is a maximum or a minimum point. You can do it by analyzing the sign. You can see the sign of the derivative between 1 and 3 divided by 2, and also you can look at the sign between 1.5 and 2. But here we are lucky to have a quadratic equation for a quadratic function. Quadratic functions have this quadratic function has a minimum because the coefficient xy is positive. In that case, the function has a minimum. If it was a negative number, we would have a maximum. So that is a very basic fact we learn about quadratic functions. So Rolle's theorem is gives us a condition existence of zeros for derivatives. You don't need to do anything. You need to find an interval AB such that f of A equals f of B. So very simple condition. You need an interval, and at the endpoints of interval, function must be equal. In that case, there will be a 0 for the derivative in that interval. So here we found at 1 and 2 function values are equal, therefore it has a 0 in between, 0 in between 1 and 2. So we can make it a little bit more complicated. Let's say function values are not equal, they have different values. The function has different values at endpoints A and B. In that case, we have this C. There is a number C, so that the derivative at C equals this ratio. What is this ratio? This is the difference of function values at endpoints divided by difference of x coordinates. So y coordinate difference divided by x coordinate difference. This is a slope of something. I can show you the picture that you should have in this that you should have in your mind for this case. So think about this. So this is f of a at a. This is the y coordinate at b, f of b. Then f of b minus f of a divided by b minus a is the slope of this line. Slope of this line is f of b minus f of a divided by b minus a. Now, what the theorem says, there is a line, there is a point C, there is a point C in between A and B such that the tangent line at C has the same slope. So tangent line has the same slope. When they have the same slope, they are parallel. These two lines are parallel. In the Rolle's theorem, what happened was f of a equals f of b. Therefore, the line joining the endpoints is a horizontal line. In that, there is a point in between A and B at which the tangent line is horizontal. So the Rolle's theorem is a very special case of this theorem. This is called the mean value theorem. Sometimes people call it Lagrange's mean value theorem, to honor the mathematician who found this theorem. So this is in geometrically very simple. Also, it has a lot of applications. We'll learn some of those applications along the way. So, picture to think about this, picture to imagine. Most of in this class, we won't go to deep applications. Most of the time, you will function f and numbers a and b, and they will ask you to find number c. All right. Given f of x equals 5 minus 4 divided by x, find all the values of c in the open interval 1, 4 such that derivative at c equals slope of the line joining these endpoints. So first of all, since we have this function, we can compute slope of the line joining endpoints. F of 4, substitute 4 into this equation. So 5 minus 4 divided by 4, that means 5 minus 1, that's 4. So f4 is 4, and likewise f of 1 is 1. So slope of the secant line joining n is 1. Now f satisfies the conditions of the mean value theorem because now the function is differentiable. You can differentiate it at any point except at 0. 0 is not in domain of this function, so we cannot talk about the derivative at 0, and everywhere else we can differentiate the function. Can you differentiate this function and tell me the derivative? I can give you 30 seconds. Please differentiate this function and type it in the chat. Type the answer in the chat. Okay. I have 106 students in the class right now. And I only received 6 answers. Anyway, yeah, all of you got it correct. Now we need a point C such that derivative at C equals 1. So let's differentiate and substitute C. 4 divided by C square equals 1. So when we solve it, we get C plus or minus 2. And we are trying to find a C value in between 1 and 4. So clearly it must be positive 2. So C equals positive 2. Find the number C specified by mean value theorem for x square on the interval 1, 2. Can you quickly do this example? First of all, you need to find slope of the line joining endpoints. Slope of the line joining endpoints. I'll show you that computation. Y coordinates at endpoints are f of 2 and f of 1. So we need to divide their difference by x coordinate difference, 2 minus 1. F of 2 equals 4, f of 1 equals 1, because the function is y equal x squared. So substitute everything and divide. We just get 3. Now find a value c such that derivative c is 3. Right, very good. I got another, again, I got 6 answers, only 6. Good. All of you got it correct. Okay. Yeah. Thank you, Christina and Nora. Good. All of you got it correct. C equals 3 divided by 2, 1.5. So we can conclude that there is a value um, C satisfying this mean value theorem on the given interval. Um, okay, here is uh, a different um, different application of mean value theorem. The mean value theorem sometimes helps us to estimate the value, estimate unknown function value. Let's say function is differentiable. That means derivative exists everywhere, and derivative is always um, bounded above by 3. That means it is at most 3, or it cannot exceed 3. And let's say f of 0 is 1. How big the f of 2 can be? So at first we don't have any idea how can we use the derivative to estimate the unknown function value. One thing we can do is we can try to apply the mean value theorem, and let's uh, keep f of 2, the unknown function value, in the equation, and let's see how far we can go. So slope of the line joining endpoints is f of 2 minus f of 0 divided by 2 minus 0. So we know everything but f of 2. According to the mean value theorem, there is a number c such that this quotient equals derivative at c. Again, we don't know the exact value of this derivative, but we know it is at most 3. It is less than or equal 3. So this ratio must be less than or equal 3. So f of 2 minus 1 divided by 2 less than or equal 3. Now solve this equation for f of 2. See, f of 2 is less than or equal 7. It is the maximum value that it can take is 7. If we were given a minimum bound or a lower bound for derivative, we could find a lower bound for the function value at 2. So likewise, you see, because of the mean value theorem, sometimes function cannot do whatever it wants. It has to behave. Its behavior is restricted by its derivative. Hmm? Zero derivative theorem. This is a very nice application of the mean value theorem. Let's say a function is continuous and it has all these conditions um, given in the mean value theorem. And let's say derivative is zero everywhere. If the derivative is zero everywhere, slope of the line joining endpoints is zero for any line that is zero, because the mean value theorem says always this line is parallel to some tangent line. Now what happened is all the tangent lines are horizontal. Therefore, all these lines, by choosing different values for A and B, you can come up with different lines, and all these lines are horizontal. The only thing that can happen is the function itself is horizontal. So function is constant on the closed interval AB. So we know derivative of a constant function is zero. Now, zero theorem tells us the other way. Derivative is zero, the function must be constant. So it goes in the both way. If the function is constant, derivative is zero. Now we are learning that if the derivative is zero, then function must be a constant, right? Uh-huh. Here is another application. This is called constant difference theorem. Let's say two functions share the same derivative. F prime x equals g prime x. If two functions are sharing the same derivative, that means at every x value, the tangent line uh, for f at x is parallel to tangent line for g at x. So at every point, they have these parallel tangent lines. For different x values, these derivative will be different, but both functions have the same derivative. Now, the constant difference theorem says the only thing that can happen is the f of x equals g of x plus some c. That means you take the graph of g and lift it by c units to obtain the graph of f. So when you move the graph up and down, you get parallel tangent lines. So you don't change, you are changing the intercept, y-intercept of the tangent line, but still you have the same slope. So derivative doesn't change. So if derivatives are equal, functions are equal up to a constant. So simply it says two functions with equal derivatives are differ by a constant. Is it clear? Is it clear? Okay, thank you, Ashmita. Good. Now, find the function f of x whose derivative is sine x and whose graph is passing through the point 0, 2. Okay. It is a very interesting problem. We have a function, unknown function, whose derivative is sin x, and whose graph passing through the point 0, comma 2. We know derivative of cosine x is sin x. And other than cosine x, there can be multiple of many other functions with the same derivative. For cosine x, derivative is sin x, but uh, there can be other functions with the derivative being sin x. Okay? So we are going to find one of those. The constant difference theorem says if two functions share the same derivative, one is they are equal up to a constant. You can obtain one by adding some constant to another. So f of x equals plus c. So here we have a function whose derivative is sin x, and we already know a function whose derivative is sin x. So this unknown function must be cosine x plus some constant c, because they have the same derivative, sin x. Therefore, I made a mistake. Derivative of sine is cosine. Derivative of cosine is minus sin x. So to have sin x, we should differentiate minus cosine x. So our unknown function is minus cosine x plus some c. So we are almost done. The only thing is we need to find this c. C is still unknown. For that, we can use this other piece of information. The graph passes through the point 0, comma 2. Means when x equals 0, y coordinate is 2. So let's substitute 0, comma 2. F of x equals 2. Cosine 0 is 1. C is a constant. It stays like it is. Now solve it for c equals 3. So our unknown function turns out to be minus cosine x plus 3. So the derivative of this function is actually sin x. You can see, take this equation and differentiate it. You would get sin x. And also when x equals 0, y coordinate is 2. So it satisfies both of these given conditions. So this cos difference theorem and zero derivative theorem are sometimes helpful if the derivative is a zero, function must be a constant. And if two functions share the same derivative, their difference is a constant. So here we found another two applications of derivatives: mean value theorem, Rolle's theorem, and two other theorems. Right. So let's move to our next topic, section 4.3. Sketching graphs. This is a huge derivatives. By the way, all these notes are in your LMS. You should go through this and study these by yourself, because I will not be able to discuss all these materials with you. I will leave some of these topics to self-study. But sketching graphs is a really important applications of derivatives. Graphs are everywhere. You will find functions are everywhere. Every time you come up with some equation, that is the equation, the relationship between two or more quantities. Hmm? When it has only two quantities, we can draw a graph. Hmm? Um, and depending on the type of the relation between them, that means if it can be linear or a polynomial equation, um, or it can be exponential equation, logarithm equation. Sometimes the underlying phenomena is a periodic one. You will get trigonometric functions. It can be very complicated, but always we try to sketch a graph because graphs helps us to see it, visualize it. Even though the equations are complicated, by just by at the graph, we can say what happens in this region. It increases this point, it has a peak value, then it decreases, and there's to this point, and all these things. You can just see it. When you see it from your eye, you don't need to um, worry about this complicated nature of the equation. So that is why graphs are really helpful. So graph sketching is one of the most important applications of derivatives. Hmm? Um, we already talked about the relationship between nature of the function and derivative. If the derivative is positive, the slope of the tangent lines are positive, function is increasing. When the derivative is negative, function is decreasing. When the derivative is zero, function has reached to a maximum or a minimum point. Again, when the derivative is undefined, we have reached to a maximum or a minimum point, critical point. Hmm? So derivative tells us everything we know. All we need to know is um, carefully put all these informations together and graph. Um, Suppose C is a critical number. If it is a critical number, um, you might need to copy this. So say A and B are two given numbers, and C is a critical number. Let's say at this point, tangent line is horizontal. So at this point, derivative is zero. There can be four different cases. First of all, between A and C, derivative can be positive, and between A and B, sorry, B, C and B, derivative can be positive. So function is increasing, reach to a horizontal tangent line, and then again increase. So this is how the function can behave when the derivative is positive in both directions. Oh. Something like this. Then let's say derivative is plus minus. If the derivative is positive, function is increasing. And at C, we have a horizontal tangent line. Then derivative means function is decreasing. Likewise, let's say C is a critical number, so derivative is A and B, C derivative is negative, and between B and C is positive. So derivative negative means function is decreasing and C is a horizontal tangent line. Then after that function is increasing. Right? Next, we can have, so we have plus 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 minus minus plus. The other remaining case is minus minus. Derivative is 0 at C, and for the other two regions, derivative is negative. Don't draw anything. Hmm? Uh, um, let's say between A and, yeah, it is negative. So function is decreasing, reach to a horizontal tangent line. Then for some reason it keep decreasing, something like this. So the first and the last case are quite interesting. Those are called, C is called an inflection point. Um, it is not a relative maximum or a, so these are extreme points. These are extreme points, these are inflection points. So whenever you have a critical point, you look at what happened before the critical points. That means you look at sign of the derivative before the critical point, and also sign of the derivative after the critical point. Numerical values are not that important, just the sign, whether it is plus or minus. So observe the sign change around the critical point, and that will give you an idea. That will tells you how the function behaves around the critical point. All right. So that is what all these words are telling you. Once you have a picture, that is very clear. But when you start writing it up, you will see a lot of this jargon. So at relative maximum, before the critical point, derivative is negative, and after the critical point, uh, sorry, before the critical point, derivative is positive, and after the critical point, derivative is negative. Positive to negative. Uh, at a relative minimum, before the critical point, derivative is negative, and after the critical point, derivative is positive. If the derivative has the same sign around C, don't call it an extreme point. We call it an inflection point. So let's see. Let's try to apply this to a word problem. By the way, we already saw this phenomena yesterday when I talked about these extreme values, undefined points of the derivative. We already talked about this thing. This is again a sort of a reminder. So consider function x cubed minus 3x squared minus 9x plus 1. Now, if you function, it is a cubic function. In our O-level classes, we have learned sketching graphs of quadratic functions out a table. You substitute some numbers, plot those numbers on the graph sheet and join them by a smooth line, smooth curve. But it won't help us to draw complicated functions, graphs of complicated functions like this, cubic functions, fourth degree functions, because these functions are very complicated. They can have multiple turning points, multiple extreme points. So just by filling out a small table, we cannot capture everything. We may need a very big table. Even for a big table, it's not guaranteed to capture everything in the table. So, and same time, these turning points or critical points, so by using a table, we cannot find them exactly. Some of these critical points are like x equals square root 3 plus square root 2 divided by something something. Those numbers won't show up in the table. So even though you know there is a critical point, you don't know the exact x coordinate to y coordinate at that point. That is why we need derivatives. So let's take this graph function. The problem asks us to find where the function is increasing and decreasing and find any relative extrema. Take the function, differentiate it, and make it equals to 0 and solve. Because zeros of negative tells us extreme points. And we can see derivative of x cubed is 3x squared, then minus 3 times 2x minus 9. Yeah, so the derivative is okay. And 3 is a common factor. Once you get x squared minus 2x minus 3. Minus 2x minus 3. So plus 1 and minus 2, minus 3 are the factors. So we have two extreme points, if minus 1 and plus 1. Plot them on a number line. Okay. Now we need to find the sign change of the derivative in each of these intervals. These two critical divide the number line into 3 regions. First of all, a very large negative number. By very large negative number, number with a large absolute value but minus. It's minus 100. When you substitute minus 100 in this equation, the last two terms are relatively small and the first term dominates because it has the highest power. And square turns every negative term number into a positive number. So negative 100 means positive, very large number. We don't need the numerical value. Just think what happened for a very large negative number. Last two terms don't contribute that much, even though they are negative. It is a really big positive number. So the sign of the derivative is positive. Now let's come and see what happened in between minus 1 and 3. You can pick something simple like 0. When you substitute 0 into equation, you get minus, so it must be negative. Then after 3, again you can pick something like 100 or 1000 and see that the leading term dominates and gives you a positive number. So this is how the derivative changes. And in fact, see what happens, how we can see the nature of these critical points. Derivative positive means function is increasing, minus means decreasing, again plus means increasing. So derivative, so function is increasing and reach to some point at -1, and then it start decreasing. So -1 must be a relative maximum for the function. Then around 3, what happens is function is decreasing up to 3, and after that it keeps start increasing. So decrease and reach to a valley and then start going up, going down, reach to a point and start going up. So it must be a relative minimum. So -1 is a relative maximum, -3 is a relative minimum. So -1 is a relative maximum. So the graph of the function has this shape. You see my point? This is what happened at -1. This is what happened at 3. So without doing anything, just by looking at the derivative, I have a picture, I have sort of idea about how this function behaves. Is it clear for everybody? Any questions? So we found the region. Sorry. Found the regions where the function is increasing and decreasing. And we found all the relative extremas. And also we found the nature of these relative extremas. We categorized them. We identified that at -1, we have a relative maximum, and at +3, we have a relative minimum. And we also sketch shape of the graph. Right? So you don't have questions, I suppose. But if you have any questions, please ask. Huh? Don't hesitate. I know sometimes I'm going fast, sometimes I'm going slow. Every time when you find something unclear, you should interrupt and ask it. Don't hesitate to ask questions. Uh-huh. So our next topic is also important. Concavity. Concavity means this is a really good parameter that determines shape of graph. So let's talk about this. Concavity. There are two types of concavities. Concave up or concave down. Let me show you. Let me draw you these two pictures. So graph is said to be concave up if the shape looks like this. Concave up. It is facing upward. Or we say it is concave down. It is looking downward. Near a sometimes it may look something like this. Here again, it is facing upward. Here we have a turning point, here we have a turning point. And in the other picture, we don't have a turning point and still came up. I can draw a similar picture for concave down. Hmm? Concave up means whenever I draw a tangent line, the graph is above the tangent line. Over here, for concave up functions, graph is above all the tangent lines. For concave down, uh, functions, graph is below these tangent lines. Hmm? Whenever I draw a tangent line, graph is below the tangent line. So we should have some way of recognizing concave upness or concave downness using derivatives. So let's think about this. Let me erase all these pictures. Let's draw a concave up graph, piece of a concave up graph. So it is looking up. Hmm? Let me draw a tangent line and another tangent line. You see, this one has a bigger slope. This one has a bigger slope than slope of the other one. And again, if I go forward, I get an even smaller slope. So what happened for a concave up graph is we move forward, the slope gets smaller and smaller. So that means slope is decreasing. This is decreasing. Decreasing means if I take the derivative function, it must be negative. Oh no! I made a mistake here. let me uh, let me create this. Let me create this. And first of all, let's talk about concave down and come back to this picture again. I made a mistake. Sorry for that. It is helpful to first look at um, a concave down graph. Hmm? Hmm? Think these tangent lines. Their slope is measured by this angle that they make with positive x-axis. So as we move forward, this angle becomes smaller and smaller. So in that case, their slope becomes smaller and smaller. Derivative is decreasing here. Again, it is decreasing. If the derivative is decreasing, if something is decreasing, its derivative must be negative. So concave down means second derivative is decreasing. Second derivative is decreasing. The other case is if it is concave up, as we move forward, the derivative gets bigger and bigger. This is increasing. Last time I made a mistake, derivative is increasing. If the derivative is increasing, second derivative must be positive. So concave up means second derivative is negative. Concave down means concave up means first derivative. Concave up means second derivative is positive. Concave down means second derivative is negative. So the concave is shared by the second derivative. Sign of the second derivative tells you the concavity of the function. So let's come back to the notes. If the graph lies above all the tangent lines, it is concave up. Concave up means second derivative is positive. If the graph lies below all its tangents, then it is concave down. Concave down means second derivative is negative. So here you can see in this left hand side piece, graph lies below its tangent lines and it is looking downward. In the next part, lies above the tangent lines and it is looking up. So this second derivative must be positive. Sometimes the concavity can be used to identify the nature of the critical points. Here we have a critical point. At that critical point, function is concave down, so second derivative must be negative. If the second derivative is 0 at a point, we don't call it an extreme point. Zeros of the second derivative are exactly inflection points. So right here, second derivative is negative. Over here, second derivative is positive. Somewhere in the middle, second derivative must be 0. Right over here, maybe, let's say it is the point where the y-intercept happens. That is an inflection point. It is not a critical point. Point where the second derivative is 0 are called inflection points. A point is called an inflection point if the graph changes its concavity at C. At a critical point, its derivative sign, therefore the increasing, decreasing nature or monotonous changes around that point. One side it is monotone up or monotone down, and after the critical point it may change. At an inflection point, concavity changes its sign. Second derivative change its sign. Suppose C is a critical number and second derivative is negative at that point. Second derivative means graph is concave down, function is looking downward. So you must be at a relative maximum. It must be a peak point of the graph. Imagine it. You should have a really good mental picture for this. If the second derivative is negative at a critical point, then that critical point is a relative maximum. Again, if the second derivative is positive, That means it is concave upward. Graph is looking upward. So if this happens at a critical point, that must be a relative minimum for the function. If the second derivative is zero, that we are at an inflection point. At the inflection point, uh, it may be a relative maximum, it may be a relative minimum, or sometimes it it just fails. The second derivative is inconclusive at that point. So, for example, if you think about y equal x cube, graph of this function looks like this. Um, 0, is both a critical point and an inflection point. Both function, its derivative and second derivative is 0. So this is a critical point and also an inflection point. Before the critical point, derivative is positive. And after the critical point, again, derivative is positive. At 0, second derivative is 0. Second derivative, that's why it is an inflection point. So this critical point is minimum, no a minimum. Second derivative cannot tells you whether it is a relative maximum or a minimum. So to have a good picture, you need both first and the second derivative. Sometimes it is helpful to have both. Right? Do you have any questions? Okay. We already saw inspect this function x cubed minus 3x² minus 9x plus. We identified critical points, and we also investigated the nature of these critical points using first derivative. And let's see whether we can use second derivatives. We saw at -1 the function has a relative maximum, at 3 function has a relative minimum, and let's see for inflection points. Compute the second derivative. Clearly it equals to 0 when x equals 1. Now you can 1 and substitute it into the initial function, and that will give you -10. 2 minus 3 is -1, minus 9 is minus, yep. At 1 comma -10, the function has an inflection point. Before 1, look at the sign of the second derivative. Before 1, you can take any number that is 0, it gives you a negative number. And after 1, let's say 5, 5 times 6 is 30, minus 6 positive. So 1 is an inflection point. Before 1, second derivative is negative, and second derivative negative means it is concave down. Graph is looking downward. And after 1, it is concave up. Function is looking upward. You can see it from this picture. Before one it is looking downward, concave down, and after one it is concave up. So that clearly tells us at -1 we must have a relative maximum. If it was a relative minimum, the graph, there is no way that graph is. And also at 3 it must be a local minimum. Otherwise we cannot have this concave up nature at that. Mhm. So yes, here we can use this concavity uh, to distinguish um, relative extreme points. Again, uh, let's say for some derivative, second derivative is also 0 at -1. Mhm. That case, -1 is a critical point and also an inflection point. In that case, we have a problem because the second derivative tests don't help us. We need to look at the sign of the first derivative. Sign tells us what happens at such points. Hmm? Second derivative alone cannot tell us anything. Um, if um, critical point coincide with an inflection point, the second derivative cannot tell us anything. But we can go back and look at the sign of the first derivative, and it will tell us anything. Hmm? So mm, you simply need to find all the critical points and inflection points and signs of first and second derivative. Sign is the key. Numerical values are not that important. Sign of the first and second derivatives are important. Uh-huh. Let's look at this function. X to the fourth power minus 4x cubed. Forget about this graph for a second. Let's keep our word. Can you differentiate this function and answer these first four questions? Um, so differentiate it and find where it is increasing and decreasing. Find all the relative extremes. That means zeros of the derivative, and find where it is concave up and concave down, and find any inflection points. I can give you roughly like 5 to 10 minutes. Um, please do it because chance for you to practice what we have learned so far. Find all these numbers and see whether it matches with the graph given in the right hand side. Hmm? And I'll come back in 5 minutes and discuss it. How's it going? Um, I guess you had enough time for that, and let's go through it. So, first thing, compute the derivative and second derivative. Hmm? Um, First derivative is 4x to the third power minus 4 times 3x to the second power. So 4x 12x square. Hmm? You can also compute the second derivative. Take the first derivative and differentiate it one more time. You'll get 12x square minus 24x. Hmm? So first derivative and second derivative. That's what you should compute as the very first step. Then let's compute where the function is increasing or decreasing. That means we need to analyze the sign of the derivative. Take factorize it as much as you can. Uh, at this point, it is very simple to find 4x square minus 4x square times x minus 3. So derivative zeros of the derivative are x equals 0 and x equals 3. Now take a point way below 0 and substitute it here. 4x square is positive, negative number x minus 3 is negative. So altogether it is minus. Then pick a point between 0 and 3. Let's say 1. Again, first term is positive, second term is negative. So again, it is a minus. Then pick a very large number, way bigger than, say, 100. Both terms are positive, so side. So right here, sign of the derivative change minus minus to plus. And at 0, derivative is 0. Um, so function is increasing from 0 to it's 3 to infinity, but it is decreasing from minus infinity to 3. Hmm? Um, so if you think about this, the function is decreasing before 0, and 0 we have a horizontal tangent line, then after 0 it keeps decreasing. So that means 0 is not an extreme point, even though it is a critical point. It is not a relative maximum or a relative minimum. So we can 0, 0 is a relative extreme, but 3 is something different. Up to 3 function is the decreasing, and 0 we have a horizontal tangent line, then it keep increasing. Hmm? Decrease, horizontal tangent line, and increase. So 3 is a relative minimum, and you can evaluate the function at 3 using this formula to find the y coordinate. Power is 81 minus 4 times 27, simplified, and it is minus 27. So this is a relative minimum. You can see this behavior from the graph. Until 3 it is decreasing, at until 0 it is decreasing. 0 is gives you horizontal tangent line, and after 0 it keep decreasing until 3, and 3 is, again we have a horizontal tangent line, and after that it start increasing. Hmm? So this is how it behaves. So we have answered the first two questions. Then the third question is about concavity. So that means it is about the second derivative. So let's go back to the second derivative and analyze its sign. So again, take the expression for the second derivative and factor it. Is 12x times x minus 2. So 0 and 2 are the inflection points. Those 2 points divide the real line into 3 regions. Let's analyze the sign of the second derivative in each region, and it turns out to be plus, minus, plus. So that means before it is concave up, uh, between 0 it is concave down, and after 2 it is again concave up. So before 0 it is concave up, between 0 and 3 it is concave down, after 3 it is concave up again. The concavity changes um, at 0, and 0 is an inflection point. So here is up, then it is down. After 2, it starts looking up again. Before 2, it was looking down. After x equals 2, it is again looking up. So we have 2 points, but only a single extreme point and 2 critical points. Right? So this is how we can put all these things together and see the nature of, see how the function behaves. We, you know, even without the graph, if the graph was absent in the picture, we could actually draw the graph of this function very easily. Once we know all the extreme points and nature of the extreme points and uh, concavity, we can put things together and draw the graph. You see, uh, the important thing is we evaluated the function only at 3 points. We don't know we don't need a table at all. We evaluated function only at 3 points, three special points, and we only analyzed the sign of derivative and second derivative. So this is a very simple procedure. We could even teach this to an O-level student. We could teach them derivatives and graph teaching very easily. But the point is to teach this in such a low-level class. We need to teach them limits, continuity. All the materials come before that. Hmm? So that's quite a lot. That is why we that is what it makes it difficult to teach this in O level class. But I don't think it's impossible. We can find a way to teach this. There are ways to teach this in O-level classes or relative low grade. Hmm. So the if somebody says this is difficult, I don't agree. Um, Everyone can master this technique of graph sketching and identify the behavior of graphs of functions using derivatives. Hmm. All right. We actually made this function yesterday and we realized it in details, but let's go through it again. X minus 2 sine x. The derivative of this function is 1 minus 2 cosine x. And we found this yesterday. We were given the derivative, not the function. We were given the derivative. Um, Zeros of the derivative are the points where we have cosine x equals 1/2. Then we drew the unit circle and find that there are only two angles with this property, pi by 3 and 5 pi by 3. And before 0 and pi by 3, between 0 and pi by 3, cosine x is bigger than 1/2. This is bigger than 1/2. For example, at 0, cosine is 1. So that makes derivative is 0. I'm sorry, derivative is negative. Derivative is negative, and at pi by 3 it is 0. Hmm. And between these two numbers, now cosine x is smaller than 1 half. When it is smaller than 1 half, this 1 minus cosine x is positive. Okay, it is positive. After 5 pi by 3, again cosine x is bigger than 1 half, so derivative is negative. The best way to see this is draw a unit circle. Hmm? So now we have two critical points. Before pi by 3 function is decreasing, and thereafter it is increasing. So pi by 3 must be relative minimum. And before pi by 3 function is increasing, after that function is decreasing. 5 pi by 3 must give us a relative maximum. If somebody wants, he can investigate the concavity. So to look at the second derivative. Second derivative is 0 at different points on the given domain, 0 to pi by 2 pi. With the second derivative is sin x. Sin x is 0 everywhere on the x, all the multiples of pi. And so if you throw away these endpoints, the only meaningful inflection point is pi. If you substitute pi into this equation, you get pi again. So we can identify the regions where it is increasing, decreasing, concave up or concave down. And that's how it looks like. I'm quickly going through these examples, and I'm hoping that you will self-study these pictures, these examples later by yourself. Huh? And this is another example that we entered yesterday. We had this function. We were given of this function. I think we had not 6, but maybe something like that. Huh? So again, all the time, what we do is we differentiate the function, differentiate it for the second time, first derivative and second derivative. Then we compute all the critical points, zeros of the derivative and undefined points of the derivative. Also, we find zeros of the second derivative. So take this function. To differentiate it, you need the product rule. Apply the product roughly, simplify the derivative and make it equal to 0. And here we have two critical numbers, 0 and 1, from this formula. And among those two, 0 is quite different because at 0 derivative is undefined. So that means at 0, tangent line would be vertical, not horizontal. It is a vertical line. And before 0, if you substitute something into this formula, for a negative number, derivative is negative. For a number between 0 and 1, cubic root positive, 1 minus, so 20 times 1 minus, something smaller than 1 is positive. So between 0 and 1, derivative is positive. After 1, now numbers are positive, so cubic root is positive. 1 minus something bigger than 1 is negative. So minus plus minus. So at 0, it should be a relative minimum. and at 1 it must be relative maximum. Hmm? So up to one function is uh, up to 0, from minus infinity to 0 it is decreasing, then from 0 to 1 function is increasing, then after 1 again function is decreasing. Uh, you can compute the second derivative. Computations will be complicated because now derivative is a little bit complicated. You can use the quotient rule, and this form, the final answer tells us second derivative is 0 exactly at x equals 1/2. I'm not going through the computation, I'm just explaining this answer in the page, but you must go through this. Hmm? At an x equal 1/2, concavity changes. Using the formula for second derivative, you can analyze the sign of that. Negative, like for a very large negative number, uh, third root is negative, but then you raise its fourth power. So denominator is positive and numerator is also positive. So concave up. Before 1/2, second derivative is positive. After 1/2, second derivative is negative. All right. So this is how you recognize the behavior of functions using derivatives and second derivatives. And by putting these information together, we can scale graphs of functions. So today we discussed three sections: 4.1, 4.2, and 4.3. And next time I will go through two of the remaining sections of this chapter. Maybe not through all of these, but you should self-study uh, 4.4 to 4.7. Those are the remaining four sections of this chapter. Uh, so maybe after the next class, I will start our last chapter. We have more chapter, fifth chapter. It is about something else. It is not about derivatives. It is a little bit different topic. All right. It is 10 past 50 minutes. This is good logical breaking point. So we'll stop here. We don't have enough time to start another topic. Yeah, this is it for today, and we'll meet later. Have a nice day.